Hi everyone. So we're going to continue today on our discussion on dot products. So yesterday we talked about we discovered these three formulas. So remember the first one basically show us how to find the dot product between two vectors if we know the length of the two vectors and the angle between them, so that we can do the cosine of that angle. This formula right here, we usually use it to try to find out what cosine of the angle between two vectors is when we're given the two vectors, so that we can also find the length. And the last one is to just be to do the inverse cosine of that. So these last two are probably going to be using mainly for either finding the cosine of the angle or the angle itself if we're given vector x and vector y. While the first one right here, is likely to find, we use it to try to find vector x dot vector y if we given the angle theta or cosine of that angle theta, and also the length of the two vectors. So they each have their own separate ways to use them. So what I want to do today would be to kind of start off with a very simple example, something that I'm definitely going to ask you to do on your next test. Find the angle between, let's say, these two vectors, 1, -1, and 3, 2. So how do we try to find the angle between them? So you will need your calculator, because you will have to do the cosine inverse. So here's how we're going to do it. So we're going to just use the formula. Cosine in theta would equal to cosine inverse of vector x dot vector y over length of x, length of y. So in this case, I can go and call the first one x and second one y. It really doesn't matter. The formula is symmetrical anyway. So I'm going to say cosine inverse of 1, -1 dot product 3, 2 over the length of 1, -1 multiplied by the length of 3, 2. So if you simply just do the dot product on the top, you have 1 times 3 plus -1 times 2, so that's 3 minus 2, so the top is 1. The bottom, the length of 1, -1 will be 1 squared plus 1 squared, then the square root of that will be radical 2. And then 3 squared plus 2 squared is 9 plus 4, which is 13. So square root of 13. And when you multiply radicals together, they just combine, so become radical 26. And so that's basically what it is. If you don't have a calculator, you can just simply say cosine inverse of 1 over radical 26. But if you have a calculator, you find out that this is roughly about 1.373. And yes, we are going to be doing it in radian, unless the question specified that we want to do it in degree. All right. So pretty simple. I mean, you just plug in the formula, and if you know how to find dot product and you know how to find length, then you definitely know should be able to do this, and then just simply find the inverse of that. Give you an example to try. This one we're not going to do, but I will show you the answer in a little bit, so that you can pause the video and just simply try to do the problem yourself, and then see if you get the same answer. If you do, then it's good. If not, you might want to double check your work. And if you still couldn't figure out what you did wrong, then obviously ask me during class. So find the angle between 1, 3, 0, -2 and 4, 7, 1, -1. Notice that both of these vectors are in R4, but that's okay, because as soon as when we put these two vectors together and start from one point, they actually create a plane where the triangle exists and where the angle exists, so they can find the angle between them. Now, why does this two direction form a plane? Well, you learned it in 1.3, where in order to define a plane, all you need a two direction vector. And guess what we have right here? Two direction vector. So we can actually use that to define a plane. Now, of course, some of you might be thinking, but these are in R4. Well, yes, you're right. They are in R4. And so what does it actually form in R4? Well, something similar to a plane in R4. We will talk a little bit more about it when we get to chapter 2. So right now, just have to take my word for it and just kind of understand that if you draw two arrows, they would definitely be on a piece of paper, and there will be an angle between them. So if you want to pause the video, you should. I'm going to just write out the answer so that you can check your answer after you're done. Okay. So in this case, if you do it correctly, the angle theta would be approximately equal to 0.492. So hopefully you did the question correctly and get the same answer. Yes, I do like to round my irrational numbers to 3 decimal places. If the number is actually rational, then I usually try to write it in a fraction form. So that way it will be exact. Okay, so and most likely that would be what I'm going to ask you to do on your test. If you have to write out an irrational number in decimal form, you would definitely have to keep it to 3 decimal places. But you could also just write it as a using radical, or like in this case, you can just simply name it cosine inverse of 1 over radical 26. Unless the question asks you to round your answer, then that means I want it in decimal form. Then you have to round to whatever it is. All right. So now come a very important consequences to this theorem, to this concept. So now we can actually form dot product by using the angle between the two vectors. So now they actually bridge the concept of using the dot product to actually determine about angle, because I can now clearly see that I can use a formula, this formula right here, to actually find out how big the angle is by just using cosine inverse along with this part inside. And that basically relating to a dot product also. So show you what one of the most important consequences is. Note the following. If two direction vector are perpendicular to each other, then the dot product must be 0. Now, here's something interesting I want to point out. So this statement does not say that two lines are perpendicular. We talk about two direction vectors. Now, how is that different? Well, the slight difference is the following. Two directions are perpendicular, simply meaning that those two directions point in perpendicular direction. But two lines are perpendicular will require two things. So something worth writing down for yourself. In order for you to show that two lines are perpendicular, not only you must show that the direction vectors are perpendicular, but you also show that they intercept. Because that's the definition of perpendicular lines. Perpendicular lines are two lines that intercept each other and form right angles. So therefore, there's a slight difference between the concept here. We'll talk a little bit more about it, but just keep in mind, when I say two directions perpendicular, doesn't mean that because they're direction vector, they're not line, there's no such thing as intersection between them. However, if you talk about two lines are being perpendicular, then those two lines must intercept. And I know some of you are probably thinking like, well, if two lines are perpendicular, wouldn't that imply they're not parallel? And if I imply that they're not parallel, wouldn't that imply that they intercept each other? The answer is yes and no. Yes, it is true, but if it's in R2. No, it is not true if the two lines are in any dimension beyond R2. So therefore, that's the problem. See, when you're in 7th grade, when you first learn about all this, or when you're in geometry, when you first learn about all this, you're only working R2. We are no longer in geometry class. We're in multivariable calculus. So a lot of these things are now changing because now we have to consider more. Okay, so keep that in mind. You can't use your logic or what you have learned in geometry to try to completely understand what we're going to be doing here, because we are trying to move beyond what you learn at those classes. So therefore, this statement basically states the following, that perpendicular and dot product equals 0 are basically corresponding to each other. So show you how that works. So let's suppose, show you the proof. So I'm going to show proof in both directions. So the first direction is I want to prove is if vector x is perpendicular to vector y, then I want to show that the dot product is equal to 0. So if they are perpendicular, then I can say that the angle between these two vectors would have to be pi over 2. And therefore, when I do the dot product between x and y, that becomes the length of x, length of y, cosine pi over 2. The problem, cosine pi over 2 go to 0. And therefore, regardless of the length of x and length of y equal to, this dot product come out to be 0. So that shows that if they are perpendicular, the dot product must be 0. Now, let's do the reverse proof, meaning, what if the dot product is 0? Does that automatically tell me that they are perpendicular? Well, let's see. If, let's say, x dot y equal to 0, then what does that mean? Is that then imply that length of x times length of y times cosine theta is equal to 0. Problem? The problem is, as long as x is not 0, or y is not 0, then that would tell me that length of x and length of y, oops, I meant to write, and length of y are not 0. Because as long as either one of these or both of these two are not 0, then the length would not be 0. And if that's the case, then the only conclusion is that this implied that cosine theta must equal to 0, and therefore tell me that theta must equal to either pi over 2 or 3 pi over 2, which in both of these cases indicate that vector x and vector y must be perpendicular, because they either form 90 degrees angle or 370 degrees angle, which the supplement of it is 90 degrees. Or well, naturally not supplement, but the other part of the angle will be 90 degrees. So in both of these cases, which demonstrate that the two direction vector are perpendicular. So now show you another way to use these formulas. So one of the very popular questions that I'm going to ask you to do, which I actually likely ask you to do that on your test, is this one. Find the largest angle in the triangle whose vertices are given by the position vector. Note that I didn't say coordinates, because then that will require me to kind of tell you what the basis is, or you're going to have to assume that I'm using a standard basis, which yes, you will most likely be the case if I don't specify a basis. But I'd rather just use position vector, because then that way I don't have to worry about getting into that whole thing. -2, 3, 1, 1, 0, 1, and 2, 1, 0. So how do we go ahead and find the largest angle within this triangle? So the way to do that is to first identify the longest side. And here's where students make mistake. Because the students see, oh, there are 3 vectors here, so now I can find the length of them, and that will give us the longest side. Unfortunately, no, that's not the case. Why is it not the case? Because these are position vector. So these are basically vectors that kind of tell you where the vertices are. But it did not tell you the triangle. So think about it this way. Let's say here is the point of reference. Here's my origin. Then these 3 vectors, I'm going to call this one vector A, this one vector B, this one vector C. Then this would probably be like vector A. This will probably be like vector B, and then this might be vector C. Notice that they don't form a triangle together. Of course they don't, because they are all position vector. And what does the word position vector tell you? Is that these three vectors must all start at the origin. And if that's the case, they can't form a triangle. Because the key of a triangle is that you have three lines that connect 3 points together. But this particular case, all three lines or all three vectors are pointing in the same points. So then where the heck is the triangle? Did I give you a wrong problem? No, here's how it worked. So imagine point A, vector A, identify the point A right here. And this identify the point B. And this identify point C. So now those 3 points. Oops. All right, let's see if I can do better. Yeah, as I say, it's kind of hard to draw a line to a specific spot. There you go. That is my triangle. The triangle that goes through the 3 end point of these 3 position vectors would be what formed the triangle. So now the question then comes, how do I find out the largest angle? Now in this picture, that clearly seems like B is the largest angle. Actually, I have no idea. And this picture is probably not drawn to scale, so it's probably not true. Not to mention perspective and stuff, so it might not be the largest angle. So how do I actually mathematically figure out? Well, by identifying the longest side. So what I need to do is figure out how long each of these sides is. And the question is, how do I do that? Well, you already know how to do that. It's right here. This picture. If I know the 2 lines that form the side, I can just do subtraction to figure it out. So that's what we're going to do. In this picture, I'm going to say this line right here that go between A and B is the vector A minus B. Now, it really doesn't matter which way you subtract, because we're looking for the length anyway. So I'm going to just do A minus B. And how about this one that go between B and C? Well, I'm going to go and say this is B minus C. And the one that go from A to C, I'm going to go and call that A minus C. So those are the 3 vectors that kind of show what the direction is between each of these vertices. And therefore, their length become the distance between these 3 points. And therefore become the length of each side. So therefore, what I'm going to ask you to do is go and find out how long each of these 3 vectors are. And you definitely don't need me to do that, so go ahead and try to figure that out on your own. You can pause the video and then try to do that before I write down the answers. So if you do that correctly, A minus B, or if you choose to do B minus A is the same exact thing, would be radical 13. B minus C or C minus B would be radical 3. And then A minus C or C minus A would be radical 21, which in this case, that makes this the longest side. So the angle that's opposite to A minus C will be the largest angle. So how do I find the largest angle? I need to use the 2 vectors that form that angle. So in this picture, A minus C is right here. And the angle opposite to that is vertex B, which have A minus B and B minus C as the 2 sides. So we're going to use that to help us figure out the angle. So angle theta, we go cosine inverse of vector B minus C dot product vector A minus B over the length of B minus C and the length of A minus B. So this is actually pretty interesting, because if you do it correctly, you already know the bottom. The bottom will be radical 3 and radical 18. But the dot product between B minus C and A minus B are actually 0. And guess what? What does that mean? Well, that simply means if the dot product of the 2 vectors is 0, that means they're perpendicular. So I can now conclude that the angle must be pi over 2. Now it says shocking. Well, actually, no. Some of you who might already noticed it. If you look at the three lengths that we figured out, right there, notice that they actually satisfy the Pythagorean theorems. Okay, so if you think about it, just think about this right here. If I take radical 18 square plus radical 3 square, guess what? That's just equal to radical 21 square, because 18 plus 3, which is 21. So since it satisfies the Pythagorean theorem, it must be a right triangle, and therefore the largest angle of a right triangle must be 90 degrees, or pi over 2. All right, interesting. So in this case, be very careful. You will see me ask you this question. Why? Because I like to ask this question so that I can see whether you understand that when you're given position vector, those position vectors do not describe the side of the triangle. See, that's a very important concept that you have to understand. I mean, anyone can plug in numbers into a formula. But if you don't understand what you're plugging in, or you don't understand the concept behind it, that's where you make a mistake like this. Because if you think about these three position vectors, you know it doesn't make sense to use them, because they would not form a triangle. So that's a very important thing. Okay, so keep that in mind. Make sure you understand, because you will see a problem just like this on your next test. Now, the next thing I want to talk to you about is the following. The next thing I want to talk about is to introduce a concept called unit vectors. So if you recall, in the beginning of this 1.1, I told you that a vector is a geometrical object that can identify two things, a direction and a magnitude. And the problem is that a lot of times we're using vectors just simply to try to convey the idea of the direction, and really doesn't want to talk about the magnitude or use the magnitude the other way. Now, with that being said, magnitude of a vector does serve purpose. And we will talk about some very important interpretation of what the magnitude of a vector is. But also in a lot of cases, all we really want to know is the direction. We don't really care about the magnitude, which is basically the length. And so what we want to do is to choose a vector where the length would not kind of mess up problems that we're going to do, because we don't have a meaning for them, and we don't want it to somehow mess up our math. So the way to do that is to define direction using what we call unit vector. So what is an unit vector? An unit vector is basically any vector whose length is equal to 1. So what's so special about the number 1? Well, the number 1 is called multiplicative identity. So anytime when you multiply something by 1, it stays the same. And what we go eventually learn about is that the magnitude of a vector has a lot of application in physics, which require you to multiply the length by something else. And so in some cases, if I want to only talk about direction, I want the length to be just equal to 1, so that if I do have to multiply it by something else, it doesn't change what we multiply. So it doesn't mess up the math. And also another thing that we're going to use is the following, which you probably remember hear me say this in 1.3, where I say that the direction vector of a line or plane is basically kind of like the step that you're allowed to take. Or we also talk about something similar to that in 1.1, where we're talk about bases and coordinates, where you're kind of using the basis to kind of count how far you have to go to a certain spot. And so with that being said, then it's easier to use direction to have a unit length, or length 1, because then that just corresponds to counting, like a counting number. 1 step is 1 unit long, 2 step, 2 unit long, 3 step, 3 unit long, and therefore make it easier to kind of identify distances by doing that. Same exact idea as if you're using a ruler. It makes sense that for your ruler to just basically count by 1, so that therefore easier for you to count to measure something. Imagine you have a ruler where each tick mark has different length between them, then it will be very difficult for you to actually use it to count. So that's one of the main reasons why we use unit vector. But of course, there's a problem. The problem is not many vectors that we use have unit length. As a matter of fact, I'm going to say that most vectors that we use not have unit length because they have way more other real numbers than the number 1. So therefore, is there a way to force a direction vector to have a length of 1 to make it into a unit vector? And there is. That process is referred to as normalization. Normalization. So normalization basically meaning that you try to normalize a vector, and the word normalize in this case meaning create a direction vector that have the same direction but length 1. So when given a vector, we can create a unit vector in the same direction. So the process doesn't change the direction of the vector, but simply changes length to 1. By doing this process called normalizing. So how do you do that? So actually pretty simple. If you think about it, you already learn about this in 1.2. In 1.2, we learn an operation that has the effect of changing the length of a vector without changing its direction. And what is that operation? Scalar multiplication. So basically what we have to do is simply multiply the vector that we given by just the right number. And therefore make it into a length 1. So how do I know what the right number is? Well, let's say. So let's say given a vector x in Rn, and unit vector u in the same direction as x is given by the formula right here. So how do I find vector u? Simple. I simply take vector x and multiply by some scalar to allow me to scale it down to length 1. So how do I do that? Well, simple. If, let's say for instance, if this vector x has a length of 3 right now, how do I make it into a length 1? Well, by multiply by 1/3. So that way, if I make the vectors, if I multiply this vector by a scalar 1/3, that would scale its length down to 1/3 of whatever it was. And if this vector have a length 3, then when I multiply by 1/3, it just make it become length 1. What if this vector have a length 5? Well, simple. Then you multiply by 1/5. So therefore, it seems to me that the scalar that we have to multiply is simply just so happen to be the reciprocal of the length. And it makes sense because you multiply by the reciprocal of the length. Then when I calculate the length, then the length of x will just cancel out by its reciprocal and therefore give you 1 always. And therefore result in this formula. To form the unit vector of a given vector x, you just simply have to multiply that vector by its 1 over its length, or divide the vector by its length. I often have students who get confused and ask me this question: is the vector u the same vector u we use in the line, in the parametric representation of a line? The answer is no. Okay, please understand there are only 26 letters in our alphabet. But we will have to use variables, lowercase letter, to represent way more than 26 different things in math. So therefore, a lot of these letters are going to get reused. So you have to make sure you pay attention to how we use them so don't get confused. In this case, this vector u is called unit vector because the word unit starts with the letter u. Okay, is that the same as the direction vector in the parametric representation of line? The answer is no, it's not. Okay. However, you could use a unit vector to define the direction of a line, which is actually good and actually is sometimes referred to as normalized parametric representation of a line. So that way you're now not using the direction vector's length to affect anything in your description of the line, which that can be done. Okay, but it's not the same U. So the video is already 30 minutes, so I'm just going to simply show you a couple example on normalization. So, and then that's it for today. So let's try to normalize this right here. Normalize the vector 1, 1. So how do I do that? So let's say this is my vector x. So to normalize vector x or normalize the vector 1, 1, all I have to do is take the vector 1, 1 and multiply by the length, or divided by the length of the vector 1, 1. So therefore just be vector 1, 1 divided by radical 1 squared plus 1 squared, which is just radical 2. So there are several ways you can write your answer. One way to write the answer is write it this way. And I do prefer you to write it this way than put radical 1 over radical 2, because I do prefer to be written as a scalar multiplication. So here's my scalar, which is 1 over radical 2, and then multiply by the vector 1, 1. I would say this is a good way to represent your answer, or good way to leave it as it is if you have more operation that you have to do with this vector. Because in some cases you can keep the 1, 1 as nice integers and then just deal with the 1 over radical as a scalar. So if you have to multiply by some other scalar or doing dot product, you don't have to worry about like wacky number like 1 over radical 2. However, as an answer to its own problem, I would expect you to do this. Is to multiply out 1 over radical 2 into your vector and give me an answer in vector form with no more operation, because that would require no more operation to define this, nothing more to simplify. That's your answer. This, you can still do one more operation, and that would be the scalar multiplication. So I would say this answer is undone, unfinished. This is completely done. But if you have this and you still need to do more math with it, then I would say keep it in this form, because it's just easy to work with. I'll give you another problem. So this one I'm not going to do, but I'm just simply going to ask you to go ahead and try to do that, and I'm going to just write out the answer for you. So that will be this vector right here. The vector 1, 0, negative 3, 2. Okay? So normalize it. So if you want to pause the video, you should. So that way you can see the answer afterwards. So I'm going to write out the answer. So the answer will be this. All right, so that's your answer. And yes, some of you are probably going to ask, can we have a radical in the denominator? I thought that's not allowed. Well, you know what? It's actually okay to have a radical in the denominator. I don't see any reason to fix that unless I have to, or unless other part of the problem require me to. Otherwise, it's perfectly okay. Just leave it at that. However, I don't want you to put in decimal form. No, that's not. I don't want, because they're irrational. You'll never be able to write out a decimal form for all of these, because they're irrational, and I don't want you to run unless you have to. So I would say leave them in radical form. All right. Unfortunately, I think that's it for today. I just have a little bit more in 1.4. I'm probably going to finish up with the next video, and then that will be it. And then we're going to move on to 1.5. All right. Talk to you guys soon. Bye-bye.